Okay, it's 9:40, so let's get started. Homework score solutions are finally up, so you should be able to see them now. If not, please let me know. Homework 5 is out, and the last part is due Sunday, so no more homework after that. And quiz 12 is out. So there will be one more quiz after this. Okay. Any questions before we start? So, I should mention. Everyone, I mean a lot of people, have been asking me numerous times for a final exam review session, so your wish has been granted. Next Thursday, during class, I'm going to do a final exam review session. So, but here's the catch. I've been instructed, if there are no questions, to talk about why the sky is blue for 75 straight minutes. So if you do not want to know why the sky is blue, you may, then what should you bring to the session?
Questions.
Questions. Thank you. To aid me a little bit, and just don't throw the most obscure question right out at me during the session, send me an email if you have a question, probably 1 or 2 days before, so by next Tuesday or Wednesday, and I'll be sure to at least talk a little bit about it. Okay? Give me time to prepare.
Can you get access to the previous year final question?
Sorry?
Can we get access to the previous year's final exam?
I don't have them, and I think there's an ASU regulation for not releasing final exam. So I don't know why some professors do, but I think we're not allowed to give away final exams or solutions to them. Yeah. But the format will be essentially the same as the midterm was. Any other questions about that? Yeah, so bring questions, let me know by Tuesday or Wednesday. All right, so what did we talk about last week? Hopefully not why the sky is blue. What did we talk about?
Decidable languages.
Sorry?
Decidable languages.
Yeah, decidable languages. All right, so what was let's say one of the decidable languages we actually talked about? What was the name of one? We talked about like 6. I'll give you a hint. Starts with A and ends with DFA. So yeah, A's and DFA. You see that in the back? I'll try to do it. Your tuition needs to go more to added friends. Markers. All right. So what was this language? It was something like this. So it's machines and strings, where M is a DFA, and it's accepted by the machine. The string W is accepted by the machine. What in the world is this? Ah, some kind of description of the machine. Oh, what do we call that? Encoding, yeah. So this is an encoding. What in the world is an encoding, and why do we even need it?
So we can analyze the machine.
Sorry?
So we can analyze the machine.
Not necessarily analyze, but where am I putting this machine? Machine, quote unquote. I'm putting it on the table. Can I put a machine directly on a table? No. So what is this helping me do?
Turn it into a string.
Yeah, so it's just a string representation. Your to-string of the Turing machine, if you will. So it's a way of writing the machine and input on the table. Okay, why was this decidable? If it's decidable, it always halts. But why is it? Why does it always halt?
Because it's a DFA.
Yeah. Well, how did we? Well, it's a DFA, but how do I know it's going to halt? So, well, what was the step that allowed us to determine that W is in the language of the machine? Just run the DFA on the input. Why does that take a finite amount of time? Right, the input length is finite, but the important thing is that I consume a character every time. So how would I do that on a Turing machine? Well, if I have the DFA here and the input here, what I do is I mark the currently viewed character on the input, W, and I also keep track of the current state. And knowing those two, I can just go back, look at the transition function, and determine the next state. And then I update accordingly. Okay? When the input's exhausted, I just see what state I'm in, see if it's final state. And therefore we're done. What was another language that we saw was decidable? ANFA, and we converted it to ADFA by just converting to a DFA. So in ACFG, we saw how to simulate rules of the grammar. What's something related to DFAs that wasn't necessarily acceptance that we saw was decidable? Yeah, E, D. So what is this? What does the E stand for? An emptiness, yeah. So I want to know, oh, this guy is so bad. M is a DFA. And what do I know about it? Or what do I want to know about it? The language is empty, yeah. I am done with that. Some of you are going to have to suffer because I'm going to use red. Because it's the only color that works. Is that okay? Or okay. Sorry about that. So why was this language decidable? Well, if there's a path from the start state to any final state, what do I know about its language? It's not empty. So what I do is I turn this problem into a graph search algorithm. BFS, DFS, Dijkstra, forward focus if you're so inclined. All of those I could just see if there's any path from the start state to any final state. So that's decidable because the algorithm, those are algorithms. They terminate in a finite amount of time. This will actually be important for the rest of the problems in a bit. So it's important to understand that this is decidable. So any questions about these? Okay, so let's do this one. So these two problems I really think are interesting because they have nice applications. So why would this be useful? If you could model, let's say, a specification of a system you have to make in terms of a DFA, and you can make a DFA for your actual system, then this says that if you can determine whether or not the system that you make satisfies the specification and does nothing else. So that'd be kind of useful. And so this is decidable, I claim. So, how would I decide? So first off, what is a really, really bad idea if I wanted to try to decide this? Well, something that you might try, but it definitely won't work. What would be a counterexample to it being a subset? How about if the first machine accepts something that the second one does not accept? Is that contradicting the subset? Yeah, so maybe what I can do is just try strings, maybe all the strings like 0, 1, 2, and then keep going, if I ever see a counterexample of I have a string that's accepted by the first machine and not the second machine, I say, no, it's not a subset, and therefore I reject. Okay? Why is that a bad idea? I could run forever. If it really is a subset, I'll never find a counterexample, and therefore that strategy would run forever. So I need something smarter. What is another way to write subset of something? Well, based on the definition, everything in language of M1 is in language of M2. That's what it means to be a subset. So let's see. But it could be the case that if I have L of M2 here, then the situation that I want is L of M1 is a subset. Maybe it's equal, maybe it's not equal. But this is the situation I want. But it could very well be the case that M1 accepts stuff that M2 does not. And I want to check that, whether that's the case or not. What do I want this region right here to be?
Empty.
I want it to be empty. Oh, okay. If I model that region as a DFA, could I check whether it's empty or not? Yeah, how do you know? Run eDFA on the DFA. Okay, so how can I model a DFA for that region? Well, it's got to be an L of M1, right? That's obvious. So it has to be an L of M1 for sure. What does it have to be also? Not an L of M2. If it's an L of M2, then that's still a subset. If I have that this region must be outside of L of M2, so it must be also not in M2. And then, what do? I want to check if that region is empty, just like we just said. So I want to ask the question. I want to ask the question, is that language empty? I know how to make a DFA for that by assumption. Can I make a DFA for the complement of L of M2? Yeah, what do? Swap final and non-final states. Fine. Once I have a DFA for both parts, could I make a DFA for the whole intersection? Yeah, how do you know? Product construction. Fine. Once I have a DFA for the whole intersection, could I check whether it's empty? It accepts anything or not. Yeah, just run eDFA on it. And I know that works because there's a decider for eDFA. It will always stop. Okay, so let's write it up. So on input M1, M2, where M1, M2 are DFAs. What do I want to do first? What's the first thing I should do?
Complement.
Yeah, find the complement of L of M2. Okay, so I gotta make a DFA for that. So I'm gonna make a DFA. Now, the hardest part about this whole process is gonna be coming up with names for things. So I'm gonna call it M sub C for complement. So I'm gonna make the names as intuitive as I can, where L of MC is the complement of M2. I could combine these, this step and the next one into one step, but I'm separating everything as needed. Okay, well, once I have that complemented DFA, what do I do with it?
Product construction.
Product construction on MC and M1. Okay, and for the intersection. So make a DFA. So I'm going to call it I for intersection, where the language of this machine I is the intersection of M1 and this complemented thing that I just made. Okay. So now I do have a DFA that represents that region. What do I want to ask about it? Whether it's empty or not. So here's a point that's actually going to be really important. Can I say, so that you know what the answer is going to be now, based on my tone. Should I say run eDFA on I? No, why should I not say that? What is eDFA? So then L ends with language. It's a language. Can a language take a DFA as input? No. What takes DFAs as input? Turing machines. So I should say run the decider for eDFA on I. So and I'm going to give that decider a name. So run the decider. It doesn't have to say run, but you have to say the actual machine that's going to be run on whatever. So I'm going to call the decider D for decider for eDFA. Well, I got to present it, this machine I to eDFA, so I got to re-encode it so that it could take it again. So we know the question by now. Can D run forever? No, because I know it's a decider. So it must say accept or reject. So if D accepts, so it's pretty obvious I should say accept here, but let's go through the analysis because the next two problems we will need to do that. So if D accepts, then what does that mean about I? D says, yes, what do I know about I? This language is empty. Okay, that's fine. So if I's language is empty, what do I know about the intersection? It's an empty intersection. So there's nothing in common between M1 and the complement of M2. What should I say to the subset problem then? I should accept because this region is empty. There's nothing outside of M2 that's also an M1. So I should say accept here because it really is a subset. In the other case, if D rejects, it's pretty obvious it's going to reject, but let's go through the analysis again. If D rejects, then by a similar argument, I know that I has non-empty language because D said, oh yeah, it's not empty. So if I has non-empty language, then what do I know about this intersection? There's something in common. So if there's something in M1's language and not in M2, then there's something outside here. So what should I say the subset? I should say reject. Because I just determined it's not a subset anymore. So reject. And that's the whole algorithm. Okay? If I wanted to claim that this language was decidable, what should I tell you about this machine that I just made? It halts on every possible endpoint. Well, let's see. Does step 1 take a finite amount of time? Yeah, the strategy we talked about was flipping the final and non-final states, and that definitely doesn't take a finite amount of time because I just copied the DFA over. What about step 2? Yeah, it's product construction. The DFA is much larger, so it'll take longer, but we can still do it easy. What about step 3? I assume it's a decider, so therefore I know it will stop. And it's pretty obvious step 4 will stop too. Okay? So I can really definitely claim that this is a decidable language. Okay. Any questions about that? There's actually another strategy using EQ DFA, but I won't talk about it. But any questions about this? Okay, so that problem I really like because of the application I talked about. Here is another problem that I really like because it brings a lot of the course ideas together. So I want to decide, given a single DFA, whether it has an infinite language or not. Okay? Let's see. So how would you be convinced when you're given a DFA whether its language is infinite or not? So a common way I like to phrase is that your friend, who isn't good at the class, obviously by now, he has a DFA, and he tells me that, yeah, the DFA I have has infinite language. What should I say to him?
Prove it.
Yeah, prove it. Show it to me. Convince me why that's true. What could he do to convince me? How would a DFA have infinitely many strings in the language? It has a loop.
It accepts everything.
Well, it doesn't have to accept everything because it could accept 0 star 1 alphabet 0 1, for example. But if it has a loop, and what do I need to know about the loop? The start state better be able to get to that loop, and some state in that loop better go to any final state. So we have a situation where we have the start state is allowed to go through a loop, and some state in the loop is able to go to a final state. Right? That's the situation we have. If we have a situation like this, the language is definitely infinite. Does this remind you of anything at all? Yeah, what? It's coming back for vengeance. Yeah, pumping lemma, right? So this brings up something that's actually going to be very important. So pumping lemma is actually very helpful in proving language is non-regular, but it's also really important here as well. So let's see. So it said that for all W in whatever language we're talking about, with length at least a certain number of p, we have W is x, y, z, so that x, y has length at most p. So this condition will not actually be very useful, but the second condition, y being non-empty, actually will be very important. And the other condition is that if we pump in as many as many y's as we want, then it stays in the language for all I. Yep, that's just a rehash of what we've been. Is there something about this that screams out infiniteness to you? Yeah, infinitely many I. Maybe we can get some kind of infinitely many strings based off of that. So let's see. Let's consider I copies of y, and then the same string, but a different number of y's. So I have two strings, exactly the same x and y, x and z on both ends, and a different number of y's in the middle. What do you know about those two strings? What can you infer? Do they have the same length? No, because y's length is not empty. Can those two strings be the same? Because they don't have the same length, they can't. So I know these two strings are different. Okay? Oh, what does that tell you about that statement then? What's that? I'm not worried about this here, I'm worried about this one. Well, y to 0, y to 1, y to 2, ... Are all those strings different? Yeah, because I put in an extra copy of y in, and y is not empty. So, if I can get to this point right here, the language must be infinite. right? It must be infinite because if I can get a W that's like this, then I can pump as many times as I like, and therefore the language is infinite. So that sounds like a problem, because I do have DFAs that have finite language, for sure. So what went wrong? Nothing about our analysis was wrong. It was actually one word, very short word. If. If there is such a string of length at least p, then we have an infinite language. What if there wasn't one? If there was no string of length at least p in the language?
And it's finite.
What's that?
Then it's finite.
It must be finite. How many strings are of length at most p minus 1? Finitely many. There are only finitely many strings up to a certain length, so therefore the language must be finite. So if I can determine if there's some string of length at least p in the language or not, then I can decide whether the language is infinite or not. Okay? Pretty cool idea. But what is that number? Well, it's guaranteed to us by the pumping lemma, but for DFAs, what is it? Or make it easier, how did we guarantee that there was a loop when we fed this string in?
Pigeonhole. The pigeonhole.
Pigeonhole principle. So what should I make P then? How about the number of states in the DFA? If I feed a string of length exactly equal to the number of states or more, will I guarantee the loop? Okay. So this, in my mind, represents number of states in DFA. So if I'm given a DFA as input, can I determine the number of states? Certainly. Yeah, I just write down, for every state I see, just write down the counter. Okay. Once I know that number, let's say it's 3, for instance, can I make a DFA that accepts exactly the strings of length at least that number? Yeah, so if P happened to be 3, for instance, and the alphabet was 0, 1, then what I do is just have a chain of length 3. Right? So this accepts exactly the strings of length at least 3. Okay? Of length at least 3. Okay, well, let's see. So this is building all to this. What I want is the strings in the language of the DFA that I've given and are in here. If there's anything in that intersection, what do I know about the language of the original machine? It must be infinite, because it accepted something of length at least that number p. If that intersection was empty, then it accepts nothing of length at least p, so what do I know about the language of the input DFA? It must be finite. Do I have a way of checking whether a DFA's language is empty? Yes. So, isn't it amazing that all those ideas combine together to solve this problem? That's why I really like it so much. So, M where is a DFA. So what should I do as a first step before I can do anything else?
Count the number of states.
I gotta know the number of states. I can't make this thing without the number of states. So let's figure out the number of states. So let n, I'll let it, I should do p instead of be consistent. Let p be the number of states in M. Well, P might not be 3 in this case. It could be 10 trillion, for instance. Can I make a DFA for a given value of P that accepts strings with length at least that number? Yeah. So what I do is I just extend this chain as long for that number. And that clearly takes a finite amount of time because I can just keep doing this transition over and over. So make a DFA. So I'm going to be helpful in the notation. M sub greater than or equal to P, where, sorry, not where, that accepts exactly the strings of length at least P using M's octet. So I have to be careful here. I can't just say exactly the strings of length at least P because that could be interpreted to mean the strings of the Turing machine that I'm actually building, not the actual DFA that I'm taking as input. So I have to say using N's alphabet there to be consistent. Okay, well, once I have that thing, what do I do? What do I do with those two DFAs? I want the strings in M and have length at least P. Intersection. Just like we did. So, make a DFA. I again for intersection, where the language of I is the intersection of the original machine and this thing that we just made. At least. Okay. So that's just the idea we talked about. Now what do I want to know about I? The greatest English sentence I just ever said. What do I want to know about I? Whether or not it's empty. So do I run eDFA on I?
No.
No. What do I do?
On the decider.
Run the decider for it. Good. So run the, what people commonly do is they shorten that to say run eDFA, but when you're starting off, you should say run the decider for it because you want to be absolutely sure you know what you're doing. So, life pro tip right there. Run the decider for eDFA on including mine, just like we did before. And then now, since it's a decider, it must accept or reject an infinite amount. So, oh, I should give it a name, D. So if D accepts, then we say something. Then if D rejects, then we say. So it's important to actually look at the cases here because the answer actually will be reversed of what eDFA says. So let's see why. If D accepts, right? If D accepts, then I's language is empty, by definition. If I's language is empty, this intersection is empty. So what does that mean? There's nothing in the language of M and has length at least P. Oh, what do I know about the language then of M? It must be finite because if there was such a string, the language would be infinite. Sorry, the language would be infinite. So when I'm asking the question about infinite, I just determined it's finite, so I should say reject. And it will be accept, but for the second one. But let's just go through it. If D rejects, what does that mean? That says that I's language is not empty. Well, if that's true, then there's something in common between M and has length at least P. Well, by our earlier analysis, we know the language must be infinite. So for this, because I'm deciding infiniteness, I must say accept. Okay. Any questions about that? So, can I claim that this language is decidable yet? No, what should I convince you of?
Each session.
It runs in a finite amount. Well, correctness is no problem, but runs in a finite amount of time. Do we need to do that? Can I find the number of states in a finite amount of time? Yeah, it's just going through the list of states and then just keeping a counter. That's easily done. What about that one? Yeah, if I have a, so the important thing is that I know the value of P in advance. If I know that, then making a DFA like this is no problem at all. Oh, I think these last three steps, we kind of already did. So I can claim all three of those run in a finite amount of time. So that language is decidable. Any questions about that? Yeah, I really like how all those pieces fit together, and it's a pretty cool problem, trying to decide between this. And the really nice thing is that it works exactly the same way if you wanted to do PDAs. The constant is much larger, but it works exactly the same. All right, so let's do the third. Is it something I said? It's always something I say. Keep forgetting which one it is. I wrote it and I keep forgetting. All right. So DFAs are our pals, but we gotta look at this language anyway. So language of all DFAs and L of M contains at least one palindrome. Okay. And I claim that this is decidable. So maybe we can try an idea like that last one, where I let P be the number of, not necessarily P be the number of states, but I make a DFA for the set of all palindromes, and then what I do is I do intersection, and then run a DFA, and then we just figure out what to accept or reject again. Would that idea work? I claim no. Why won't it work in this case? Can I make a DFA for the set of all palindromes? No. Why? It's not regular. So I can't make a DFA for it. So are we dead in the water? Yes, obviously. No, we're not. So is there some kind of model, not a DFA, that I could recognize palindromes?
Yeah.
Yeah, so what's an easy one? How about a CFG? Can I, for example, if I have palindromes over 0, 1, can I make a context-free grammar that recognizes palindromes over 0, 1? Yeah, same character on both ends. What must be in the middle must be a palindrome. So one way you can do it is this. Same character on both ends. What's in the middle must be a palindrome. Now we gotta handle base cases, but those are pretty easy. It's either empty or a single character. In the case of odd palindromes. So I can definitely make a CFG for this. By that reasoning, can I make a PDA for this? Yeah, all right. But I still want to do this strategy of intersection with the input DFA. Do I have a way of doing intersection with PDAs and DFAs? Yeah, we actually talked about it. So what we do is exactly the same as product construction, except what you do on the transitions is exactly what the, what you do on the transitions is exactly what the PDA would have done on the stack. Because the DFA is just a PDA that doesn't touch the stack. So we get closure under intersection, intersection with regular languages. Okay, well, let's see. Maybe we can try that idea. So on input, M where M is a DFA. So what do you think would be my first step? Yeah, I could make a CFG for the palindromes over M's alphabet. So make a CFG for that accepts exactly the palindromes over M's alphabet. Because I gotta say what alphabet I'm going over. Okay, well, and I better give it a name. I'm gonna call it G, because I'm gonna be using it. Well, what should I do with G now? Well, the strategy we talked about was with PDA. Oh, can I convert that CFG to a PDA? Yes, we talked about an algorithm for it. See how everything's coming together? So convert G into an equivalent PDA. I'm going to call P. Okay. Now what am I going to do with this PDA? I'm going to do intersection with the input DFA. What am I going to get out of it? PDA. So I better not be sly, I guess, and say, oh, make a DFA for the intersection. I'm actually going to have a PDA. So make a PDA. I'm going to call I for intersection, where language of I, like before, is the language of N, intersects the language of G. That's just the idea we talked about. Well, should I run the decider for eDFA on I in this case? It's not even a DFA. Do we have an emptiness decider for PDAs or CFGs? Well, it seems hard for PDAs because we have, if we try to do the breadth first search type approach, then the stack might come into play at that point. And then I don't know if it'll be empty or not. So, what should I do? Well, we'll have a PDA right now. Actually, you're right, that would work. But, and then I can do breadth first search. But assuming I don't do that, what can I do instead? Do we have a decider for checking whether a CFG's language is empty? Yeah, we talked about it. So I'm not going to give you the whole idea, but because there are many details to check. But the idea is, if there's a variable on the right-hand side of a rule that's not on the left-hand side of a rule, is that variable useless? Yeah, it's completely useless because it'll never generate anything because it's not on the left-hand side of any rule. So what can I do? Delete it and delete every rule that contains it. Okay? Then do it again, and again, and again, and again. As long as there's such a variable on the right-hand side, not on the left side, keep deleting rules and the variable itself. If you ever delete the start variable, what should I say? The language is empty. So that idea does not work in general, because I could have something like this. The language of that grammar is empty, but what's on the right-hand side appears on the left-hand side, so I can't delete the start variable. So there's a little bit more work to this, but that's the essential idea, and I claim we can decide that. But that's a CFG. I have a PDA. Again, are we dead in the water? No, what can I do? Convert it. Okay, so convert I into an equivalent CFG. Now I can't choose G again, so I'm going to use H. And then now we have a supposed decider for E, CFG, and I'm going to feed H to it. So run the decider for E, CFG on encoding of H. I claim this a decider, so it must accept or reject an finite amount of time. So if I should say what the decider name is. I'm going to call it D. So if D accepts, just like before, or if D rejects. Well, if it accepts, so let's go through the steps. If D accepts, then H's language must be empty. But since I is equivalent to it, it's also empty. If that's empty, empty intersection like we had before. So language of M, and it has no palindromes in it. So what should I say to palindromes? Reject. Because I just determined that my input DFA had no palindromes in it. So reject. If D rejects, then H's language is not empty. That means I's language is not empty either. Something in common between these two, because it's not empty. So language of M, language of palindromes, there's a palindrome in M's language. And by that reasoning, I should accept it. So let's convince ourselves that it runs in a finite amount of time. I'm assuming that we have a decider for this. So this is hinging on the assumption. The book has all the details of that decider, so I'm not going to go through that, but I'm assuming that that is a decider. Does step one take a finite amount of time? Yeah, once I fix an alphabet, it's pretty easy how to do something like this. Just add rules as necessary if you have a larger alphabet. Does step two take a finite amount of time? Yeah, it better, right? Because we gave an algorithm on how to convert a CFG to a PDA. Does step three take a finite amount of time? Yeah, because it's essentially product construction. That's no problem at all. Step four. What about that one? Yeah, it takes a really long time, but it takes a finite amount of time. So that's good. I assume step 5 works, and then therefore step 6 works too. Cool, so I can claim that that language is also decided. Okay? Any questions about any of these? So yeah, bring questions for next Thursday, and I'll see you next week.